Thank you very much. So many thanks for the invitation and for organizing this very interesting workshop. So I want to discuss about some aspects of sort of blending data with models. In the case where the model that to which we want to fit the data that is available to us is actually not compatible with the data that we have. So we are given, so the setup that I will consider is the following. So we are given a long time series, if you like, from, say, molecular dynamics simulations, that in principle it corresponds to a high-dimensional deterministic or possibly stochastic system. That we might be, it might be the case that we understand the physical laws that describe the full dynamics of the system, if you like. But the problem is that the full dynamics is very complicated. So we want to use the data in order to extract a low-dimensional, coarse-grained model that describes appropriately some selected degree, the evolution of some selected degrees of freedom that we're interested in. So if you like, in this atmospheric science framework that we heard Sebastian talk about, so this would correspond to the distinction between weather and climate, if you like, degrees of freedom. Okay, so the main difficulty that I want to discuss about is what happens when the available data is actually incompatible with the desired model at small scales, and how to actually circumvent this difficulty. And I want to describe to this sort of problem in some particular examples, in particular molecular dynamics. And in the second part of my talk, I will discuss about a simple model for urban structure. Okay, so if I want to be a bit more precise, so the situation that I will consider is the following. So I'm given a dynamical system that I will write in this form here. So this can be finite dimensional, or it can be infinite dimensional. It can be deterministic, or it can be stochastic. And Z evolves in a phase space Z that can be, again, high dimensional, can be infinite dimensional. And the modeling assumption that I make is that I'm only interested in the evolution of a few selected degrees of freedom that live in this subspace X. Okay? So my assumption is that I a priori know that I can decompose the phase space where the full dynamics live into a small, low-dimensional space where the resolved degrees of freedom live, and a high-dimensional space Y in which the unresolved degrees of freedom live. Okay? So I want to postulate or obtain, using analytical techniques, a reduced model that lives in this low-dimensional space X. And then this model will be known either up to parameters or even up to sort of an unknown functional form, which I then want to estimate using data of the full dynamics. So let's again describe this in some more detail. So I'm assuming, or I assume that I can actually derive using analysis. So a reduced stochastic dynamical system that governs the evolution of the selected degrees of freedom. Now, the fact that I am coarse graining, the fact that I'm throwing away information, if you like, means that my reduced model is necessarily stochastic. Okay, one can actually formulate this as some sort of a theorem. Now, whether modeling the stochastic part of the evolution in terms of white noise, like I do here. So I'm writing here I'm writing down a standard stochastic differential equation. This is the deterministic part. This is the stochastic part. And the dynamics is driven by a Brownian motion WT. It's something that we can discuss about. But in principle, this sort of methodology that I will describe today, or if you like, the sort of difficulty of fitting data to a reduced model of this form, does not depend crucially on how I choose to model the noise in the system. Okay? So the input that I have then is a set of noisy observations of the full dynamics. I project them down onto the selected degrees of freedom. And based on this information, I want to extract information about the drift and possibly the diffusion coefficient. Okay? So I can assume that I know what the functional form of f and sigma is, in which case what I need to estimate from my data is a set of parameters theta. Or I can also think of this problem in some sort of a semi-parametric or even non-parametric way. Okay? Now, let me present a few examples where a situation of this form arises. Yeah, okay, I don't need to discuss about this. So a very simple example is the following. So I consider a stochastic differential equation of this form. So differential function, I have written things here in one dimension, but a very similar analysis is valid in arbitrary dimensions. And I assume that it has two characteristic length scales. Okay, so I assume that I have a small parameter epsilon that measures the scale separation between a small scale in the system and the macroscopic scale of observation, if you like. Okay, so if I make appropriate assumptions on this potential function v, then I can rigorously limit of infinite scale separation. This equation is drift, and so the sort of potential that you can yeah, okay, so the difficulty with this, and in fact it turns out that this will render the standard estimation procedures actually being biased, is that the time series that we assume that we're given, the time series that corresponds to the full dynamics, is actually incompatible with the data at small scales. So if I try to use all data that is available to me in order to estimate the parameters in the drift and in the diffusion coefficient, in fact, I will fail. Okay, so this is one example, if you like, where having more data is not necessarily does not necessarily improve the performance of any kind of inference procedure. And what turns out, I mean, I will present actually a precise result on this. What happens is that, in fact, I need to subsample the data at a scale that is between the smallest scale in the system and the largest scale in the system. But in practical terms, this might mean that I need to throw away like 99. Okay, so the sort of potential that you can think of is this. So I have something that looks like this. So I have several, well, at least two characteristic length scales, but I can think of situations where I have more than this. And then you can think of examples from molecular dynamics or from biophysics, if you like. And then I want to be able to compute quantities such as average transition times, binding times, the stability of different conformations, and so on, the evolution of an appropriate reaction coordinate, which corresponds to sort of obtaining a coarse-grained model based on data. Okay, so then I want to basically do, after obtaining my coarse-grained model using data, I want to be able to use this model in order to make predictions, and in fact, and also in order to be able to compute quantities such as exit times, optimal paths, and so on. Okay, so now a second example that I will revisit later on comes from paleoclimatic data. So I will present some more details later on. But basically, so this delta 18O is a proxy for temperature over the North Atlantic. And this data that I have, which is like ice core data, covers a period between 70 and 20,000 years ago. And given this time series that I have, and in fact the transitions between two states, if you like, a warm state and a cold state, I want to be able to extract the that can predict this kind of transitions, and then to be able to actually compute average exit time, so how long it takes for the dynamics to actually escape from one of these local minima. So a simple stochastic model that I can use is again of this form, so it's given by this kind of overdrawn Lanzmann dynamics. V has a bistable structure, so given that from the dynamics it's clear that there exist two sort of metastable states, if you like, in my dynamics. And my task is to estimate the parameters in this potential, the parameters that I use in order to parameterize this kind of bistable potential, plus the noise. I will show how we do this later on, but let me just comment on the fact that the corresponding potential actually is highly asymmetric, so there exists a very stable local minimum corresponding to the call dates, I believe. There is a very relatively unstable minimum here, and this is the corresponding probability distribution that, again, sort of it reflects, of course, this difference between the two minima of the potential. A similar situation arises in the modeling of passive tracers. So I'm given the sort of Lagrangian equations of motion, if you like, of a tracer in the ocean, say. So V of x and t is a very complicated, turbulent, if you like, velocity field. And then I postulate that if I look at sufficiently long length and time scales, the passive tracer performs a purely diffusive motion that can be characterized by this diffusion tensor K. Now, I'm in the same situation because the data that I actually have, or if you like, the noisy data that I have, is only compatible with the model to which I want to fit the data at very long length and time scales. Okay, so I have to then decide on how exactly to use the data that is available to me in order to estimate this so-called eddy diffusivity tensor. And what turns out is, again, I have the same problem. So I need to subsample the data. I need to throw away all data that, all small-scale data. Okay. Now, I'm sure that most of you know much more than I do about econometrics, but I want to make the link with a similar problem in econometrics, namely how to estimate the integrated stochastic volatility in the presence of market microstructure noise. So in some sense, I have sort of the same setup in the sense that the data that I have is not really compatible with my model. And there is a classic work by Aitza, Halley, and collaborators where they show that, in fact, you have to subsample the data, and then you can improve this by using appropriate, well, first finding the optimal sampling rate, then using appropriate bias reduction and variance reduction and bias correction techniques in order to be able to estimate the integrated stochastic volatility. You can set this up as a problem that is quite similar to the two previous ones. And, but sort of the main feature here is also that you need to throw away data. Okay? So if you like the sort of link between what I'm presenting here and the main theme of this workshop, which is big data, is that somehow one has to also question the quality of the data that is available. And it's not necessarily the case that sort of by using more data we get more accurate predictions. Okay, so the overall sort of modeling methodology. So we heard also in Andrew's talk that one has to blend data with models. And one possible way for doing this is the following. So we are given a set of data. Then we postulate a low-dimensional, necessarily, as I mentioned earlier, stochastic model. Now, the model that we postulate here is based on one hand on physics, but is also based on analysis. So it's based on techniques from perturbation theory, if you like, the existence of a small parameter in the model, the fact that somehow we can use techniques from analysis in order to derive a low-dimensional model in a rigorous and systematic way. Now, here we use tools from time series analysis, inference, and so on. And this enables us to choose a model. So this leads to model selection because the coarse-grained model is known up to parameters or even up to sort of unknown functions. Then we assess the quality of the model. If this kind of model validation test sort of our model does not pass this test, then we go back to our coarse-grained model. If we are successful, then we continue. And here, we can use additional tools in order to actually make predictions and to be able to compute quantities. So if you think, again, so in the example of the paleoclimatic data, once I have obtained my stochastic model, then I want to actually make predictions using this, and I want to actually calculate things. In particular, I want to be able to calculate the time it takes for the system to jump from one of the metastable states to the other. And I will show how we can do this in a few minutes. Okay, so yeah, so in the end, if you like, the outcome of sort of this procedure will be the calculation of things like exit times, critical transitions, intermittent behavior, and so on. Right, now let me present a class of models for which we can actually investigate how well standard inference procedures work, or at least the maximum likelihood estimation. So I will consider a system of stochastic differential equations that have widely separated characteristic timescales. So U and V are Brownian motions here, and I can be in arbitrary finite dimensions. In fact, I could do similar things also in infinite dimensions if I'm interested in, say, Gaussian random fields and so on. Now, the setup is such that in the limit as epsilon tends to 0, I can eliminate all this so-called fast equation for the variables x. So in this sort of decomposition between resolved and unresolved degrees of freedom, y represents the unresolved degrees of freedom, x represents the resolved degrees of freedom. And to ask is that given that using singular perturbation theory, multiscale analysis, and so on, I can indeed obtain a closed coarse-grained model for the reduced degrees of freedom that in principle will be known up to parameters. Can I then use data from the full dynamics in order to estimate the parameters in my reduced model? And I want to do this in the context of maximum likelihood estimation. So first, let me present what the functional form of the coarse-grained model is. So I can rigorously prove that I can obtain a closed stochastic differential equation. And in fact, in principle, I can also calculate the drift and diffusion coefficients, or at least I can write down formulas. Well, I mean, I can calculate them up to the solution of appropriate Poisson equations and the calculation of integrals with respect to appropriate measures. So it's quite complicated, but at least I have sort of qualitative information on the drift and the diffusion coefficients of the reduced system. Okay, so then I'm assuming now that there is a set of parameters in the drift that I want to estimate, and that I want to do this given a time series of observations from the full dynamics. So I'm given a long trajectory of the full dynamics, and I want to fit this data to this reduced model here. Okay. And I want to do this using maximum likelihood. So we already saw the formula for the likelihood function in Sebastian's talk yesterday. So I can express it in terms of the Radon-Nikodym derivative of the measure on path space with respect to the Wiener measure. I can write down this formula here. Now, this is a functional of the path z, or in fact, I will evaluate this form, the likelihood function at the path of the slow variable, so from the full dynamics. And then I want to see whether then the corresponding maximum likelihood estimator will be close to the actual values that I want to, of the parameters that I want to estimate. And the result, in fact, is negative. So you can prove in this relatively general setting that the corresponding maximum likelihood estimator is asymptotically biased. I have expressed this result in this form, so that if I take the likelihood function and I take a sort of long time average, so I'm sending the length of the path that I'm observing to infinity, which is the right thing to do. This is precisely the path, the sort of limit, the asymptotic limits in which I hope that the maximum likelihood estimator will actually convert to the correct value. And then I'm also sending the small parameter measuring scale separation to 0. So I would have hoped that in this limit, I should be able to recover the correct values of the parameters in the drift, given that the path at which I'm calculating my likelihood function as epsilon tends to 0 should be getting closer and closer to the path of the homogenized dynamics. But this is not the case. There is actually a systematic error term that you can compute, again in terms of solutions to appropriate Poisson equations and so on. And the result of this non-commutativity, if you like, or of the fact that the maximum likelihood estimator becomes asymptotically biased in the presence of this kind of multi-scale structure is actually pretty dramatic. So it's not difficult to cook up examples where the parameters that you're estimating are actually exponentially wrong. Okay? So if I go back to the simple example that I started with, if I try to do exactly what I described in this context, so I generate one long path of the full dynamics, and then I try to fit it to the homogenized dynamics, to the coarse-grained dynamics, and I do this for small values of sigma. So I do this under the assumption that the noise is weak. The parameter that I'm actually estimating, which will be this little alpha, the parameter in the full dynamics, is exponentially larger than the correct parameter. Okay? So it's an easy, we can easily prove this using large deviations or Laplace's asymptotics and so on. So, but the point is that if I use the full data that is available to me, I end up with an estimator for the coefficients that in principle can be exponentially off the right value. Well, the idea is to, as I have already mentioned, is to subsample. So I want to use the data at a time scale that is compatible. And again, in reality, this means that I need to throw away like 99% of the data or something. But in this example from econometric microstructure noise, this was already observed, that subsampling means that in principle you have to sort of use only a very, very small part of the data that is available to you. Of course, later on, when you use variance reduction techniques, you do have to use all the data. But in principle, the point is that if I want to get any kind of convergence to the correct values of the parameters that I want to estimate, then I need to subsample. Okay, so this is the discrete version of the likelihood function, and I have introduced a small parameter delta, which measures the sampling rate. So if I then choose the sampling rate to scale appropriately with respect to the parameter that measures scale separation in my model, then I can indeed estimate correctly the parameters. So again, I'm looking at the limit where the length of the path that I'm observing goes to infinity, but then I'm subsampling at an appropriate rate. So there's this exponent alpha here that has to be in the interval 0, 1. In principle, actually should be in the interval 0, 2, but I mean, it's a technical thing. And then I can prove that under this scaling, so I scale the length of the path with respect to this small parameter, and then I subsample at the right rate, my maximum likelihood estimator based on the likelihood function evaluated at the path of the full dynamics converges to the correct value of the parameters. Okay. In fact, you can test this numerically. You can, you can see that it works. The variance of the resulting estimator is quite large, so one has to combine this with variance reduction techniques. This is a separate issue. Okay, now, this approach suffers from the problem that, of course, even if you are in this kind of ideal setting where you have clear scale separation and so on, you cannot really find what the optimal sampling rate is. So for these models in econometrics, so where sort of you look at, you want to estimate the integrated stochastic volatility in the presence of market microstructure, there it is possible to get a good estimate on the optimal sampling rate. For this class of applications that are kind of more related to molecular dynamics, if you like, so problems of this form, it doesn't seem to be possible to obtain the optimal sampling rate. So you can modify, though, this likelihood estimator using techniques and by representing the drift and the diffusion coefficient in some appropriate orthonormal basis. So you can study this problem in some sort of semi-parametric framework. And if you do this correctly and you use the right kernel estimator and so on, then you can bypass this issue of having to subsample the data. So then you can, with this modified estimator for the drift and diffusion coefficients, we can actually the coefficients in this sort of multi-scale framework, given either a lot of short trajectories, so a lot of observations that are short in length, or one long observation. So before I present an example using actual data, and in the end, of course, you have to solve some sort of linear algebraic problem, but you have to regularize it and so on. So there are some technical details that are not particularly interesting. Let me present one example where this approach works. So I consider the case where the fast noise, the fast dynamics in my system is given by the so-called Lorentz 63 model. We have already heard Sebastian mentioning this. So I have the system of three nonlinear ordinary differential equations with quadratic nonlinearities that was introduced by Lorentz in 63. And I'm assuming, so I rescale things, or if you like, I speed up things. And then I consider the case where my ordinary differential equation for x is driven by an appropriately rescaled component of the Lorentz 63 model rather than by white noise. Okay? So I consider this model because for this deterministic noise. So if you like, here you have sort of deterministic chaos versus white noise. But you can still prove a limit theorem. So you can still send the small parameter that measures scale separation to 0. You can obtain a closed equation for the coarse-grained variable x. And then you can ask whether you can estimate the drift and the diffusion coefficients using data. Okay. So with this approach that I very briefly described earlier, which was actually, this was joint work with Sebastian Krumzeit and Seraphim Kaliadasis. I can actually estimate accurately both the drift and the diffusion coefficients. Okay, and in fact, you can modify this in lots of different ways. You can consider also multiplicative noise here. You can consider processes that have many more degrees of freedom. In principle, you could even consider similar questions for this so-called Lorentz 96 model, which is again a system of ordinary differential equations with quadratic nonlinearities, where the dimension of this model is around 50 as opposed to 3. Okay, so now let me revisit this example of the climate transitions during the last glacial period. So first, I will use the same data set that goes from 70 kiloyears to 20 kiloyears, because this time series that I presented earlier on, and I will show again in a few minutes, is actually very close to being stationary. Okay, so this helps the estimation procedure. And then this sort of rapid climate shifts, so what I refer to as metastability, so the fact that the system can exist mostly in two states, and then I have jumps from one state to another. It's referred to as the Danskart-Oesker events. So I want to first fit then my my data to a stochastic model. And then once I have obtained this model, I want to check whether I can actually calculate exit time. So whether I can calculate how long it takes on average for the system to jump from one metastable state to another, so to calculate the frequency, if you like, of this Danskart Oscar events. Now, so as I mentioned, yeah, I'll use the same data. And now I combine this estimation procedure with some sort of hypothesis testing, if you like. So in the sense that it's not clear a priori whether the noise in the system is additive or multiplicative. So in addition to estimating the parameters in the drift, I can also ask whether the noise in the system is additive or multiplicative. So here's then the data. Here's a typical trajectory that we generate using the model that we have obtained after we follow the estimation procedure. Here's the histogram. So remember, so I mentioned that one of the two metastable states is relatively more stable than the other. And here's the statistics of the exit times. So the agreement between the data, so you can actually calculate the frequency of escapes, of course, from this time series, and then you can compare it with what you get by calculating exit times using the stochastic model. So once we have a reduced stochastic model that describes this kind of time series, then it is possible to compute exit times by solving an appropriate boundary value problem. And the agreement is actually quite good. Okay, so how much time do I have? 5 minutes. Okay, so now let me move to the next and last topic, which is the stochastic modeling of urban structure. So this is joint work with Louis Elam, who is a PhD student at Imperial and at the Alan Turing Institute, Mark Zerolami from Imperial, and Sarah Alan Wilson from the Alan Turing Institute. And I will mostly present this paper here that appeared in the Proceedings of the Royal Society of London. Now, there is a continuation of this project that I'm sort of more interested in. I mean, I'm quite excited about. Because, so, Alan Wilson, a long time ago, in fact, so he drew the analogy between sort of a complex system in the sense of physics and sort of modeling an urban area as a complex system. So he actually even has a paper called Thermodynamics of Cities, which I think is a very nice title. And so for me, I mean, my background is in mathematical physics and statistical physics and so on, so I actually like this analogy quite a bit. And yeah, you can derive some constrained Fokker-Planck type models that are quite interesting. But anyway, so in the remaining minutes, I will focus on this paper. Okay, so I can think of an urban structure in terms of origin zones and destination zones. So if you like, this is a residential area, and this is your local shopping mall. And then you have a sort of matrix Tij that describes the flow between the origin zone and the destination quantity. And so here's so what I'm mostly interested in is trying to explain some of the data for sort of retail space in London. So this is a plot of the floor space in London, and this is, well, a log plot of this, and then this is a log plot of the density of the population in London. And here's the sort of so this I mean, all this is data and it's actually publicly available. I should have given you the link. So here's a map of the London retail structure. So this large dot here is Oxford Street. And here, this one I think is High Street, Kensington, where my university is. So yeah. So anyway, so and so you can sort of compare these with the density of population. So there are also these blue dots that correspond to residential zones. And the goal is to develop a stochastic model that somehow can describe this distribution of retail space, and hopefully also to study the dynamics, so sort of the evolution of this. So this is the part that I won't talk about that has to do with constraint maximization type arguments. Okay, so then this model that is due to Wilson and collaborators is based on this concept of demand flows. And you can write down a formula that looks like this, and there are several parameters. So I don't have much time left, but so there is certainly one parameter sort of describing the attractiveness between zones. There is there are parameters that describe how easy it is to transfer to move from a zone from one zone to the other. There is an attractiveness scaling parameter. This is a cost scaling parameter, so there is an argument, for the derivation of this type of model that is based on utility functions and so on. And then there is this quantity here that describes the net utility from transporting from zone I to Z. So the original model is basically a Lotka-Volterra model. Okay, so it's a system of ordinary differential equations that is described like this. And now what we want to do is to assume that there is uncertainty in this coefficient here. And in particular, we will add a term to this model that is related to the uncertainty in the underlying parameters. Now, we already heard in one of yesterday's talk how important sort of taking uncertainty into account is. And if we do this in the simplest and most naive way, in the sense that we model uncertainty in terms of white noise, again, you can tell me this is not a good model, but this is something that we can discuss. It's not crucial. So the fact that we choose to model the full dynamics in terms of Stratonovich type stochastic differential equations is not very crucial. So now, once I have a stochastic model of this form, I can think of it in two ways. First, I can think of this as being the actual dynamics. And this is not sort of the discussion that I want to get into today. On the other hand, you can think of this as some sort of a sampling device. Okay? So if you choose the parameters in the model the right way, then this dynamics is ergodic with respect to a probability distribution that hopefully, and if you estimate the parameters correctly, will give you a picture of this form. Okay. So let's see how we can do this. So, okay, there are several technical issues, but anyway, if I make an appropriate sort of logarithmic sense of variables, I end up with the standard Overdam Lanzmann dynamics. So I would hope then that the distribution from which I want to sample in order to obtain the sort of distribution of retail space in London is e to minus beta v, or e to minus gamma v here. It turns out I need to modify this potential term. We can do this, and then we can estimate parameters. Okay, so everything is given up to these two parameters, alpha and beta, that I want to estimate. So how much time do I have? 2 minutes, okay. And I can do this. So we assume then that we have, so for its observations here, we have a hierarchical model of this form. So actually, Andrew also showed something similar in his talk. And then we need to estimate the parameters alpha and beta. Okay. Now, there are several issues in terms of how to do inference for this model. But yeah, you can see that somehow this model in principle could support structures, if you like, that appear to be relatively similar to what we actually see in practice. And yeah, okay, so the estimation procedure is done within this Bayesian framework that we have heard a lot about, of course, in this workshop. And maybe I should just present some data. So if I now, the one parameter that we play with is the strength of the noise. And in order for this kind of Overdam Lanzmann dynamics type model to give sensible predictions, we actually need to assume that the noise is actually quite small. So this corresponds to a noise strength of 10 to minus 4. So if you do this and then you do the appropriate estimation procedure, so then you get reasonably good estimates for the parameters alpha and beta. And then if you draw, if you look at the realization of the corresponding distribution, it looks like something like this. So then again, this would correspond to Oxford Street and so on. If we increase the strength of the noise, then of course the estimation procedure is not that good. So we have quite large variance. It's something to discuss. But in principle, a model of this form, where we basically start with the Harris-Wilson model, and then we add noise to it, and then we estimate the parameters using data, appears to give sensible results. Again, there are many ways one could extend the model and also the inference procedure, but I think this is a good starting point. And I think I will stop with this figure. Thank you.